everyone. We just heard an excellent ITC colloquium by Kevin Heng, visiting us from University of Bern and in Switzerland. And actually, he will speak in a few minutes as the second speaker in this lunch about a new baby that he had a few months ago. He will dedicate 10 minutes to that baby. And a baby is a metaphor. It actually is a book. It's a book that came out, and instead of taking 9 months, it actually took him 2 years to complete with Princeton University Press. It's a book about stellar planetary atmospheres, and he will talk about it and show us the content of that book. We will start with a graduate student from Caltech, Xiangcheng. He is a student of a former student of our department, Phil Hopkins, and he will talk about simulating galaxies in the Reionization era with realistic feedback. And then we'll hear from Kevin about his book. And after that, from Reinout van Weeren from the CFA, that will talk about hunting for AGN Fossil Radio Plasma with LOFAR. And finally, we hear from Azadeh, Moradinezhad from Harvard. Where is he? She? Oh, are you from the physics department?
Yes.
Yes. And she will talk about the signatures of extraparticles during inflation on clustering statistics of galaxies. We'll start with Xiangcheng.
Okay. Hi everyone. My name is Xiangcheng. I'm a grad student at Caltech working with Phil Hopkins. Today I'm going to talk about the recent work I did with the state-of-the-art cosmological simulations at the epoch of reionization. Here is a history of the universe. After the recombination happens, where we have the CMB and there's a large redshift range of dark age, where we have nothing in the universe but the neutral hydrogen. And the first stars start to form at redshift 30-ish. And then the universe becomes from fully neutral to fully ionized by redshift 5 when the reionization completes. Galaxies in this redshift are believed to be the dominant source of cosmic reionization. The next generation of ground-based telescope and space telescope, one key science for these facilities is to observe galaxies at these redshifts. They will probe these galaxies in a rest frame optical to IR with higher resolution from 200 to 400 parsec per pixel, and they can also take spectrum for galaxies at this redshift in rest frame optical. This is the current understanding of the galaxy population at these redshifts, which is the UV luminosity function. The UV luminosity functions at these redshifts are relatively well constrained at the bright end, brighter than -17. Different surveys and different fields agree generally with each other. But one problem at these redshifts is the finite behavior of the UV luminosity function. As pointed out by Richard Bowen and his collaborators, the finite behavior of the UV luminosity function is still pretty constrained. And also another problem at this redshift is the stellar mass function. Although the UV luminosity function, different groups have very relatively consistent result, but the stellar mass functions start to diverge between different groups. The current status of the theory on this side is cosmological simulations. There are basically two categories of cosmological simulations at this moment. One is large volume cosmological simulations. There are several works by Nick Nadian, Kristen Finlater, and other people targeting the redshift range that reionization happens. And also there are more general simulations like the Illustrious and the Eagle group that can simulate large volume cosmological simulations to redshift 0. But the problem for these simulations is the resolution. Although they have thousands and tens of thousands of galaxies in the box, the resolution is 10 to the 5 to 10 to the 6 solar mass for baryons. So the structure of the galaxies are poorly resolved. On the other hand, there are groups that simulate first stars formation and first galaxy formations by John Weiss and his collaborators. But these simulations usually probe only pop 3 stars and the tiny galaxies at relatively high redshifts. So these galaxies are not likely to be detected by JWST and future observations. What we do is using cosmological zoom-in simulations. The basic approach is we run structure formation from redshift 99 to redshift 5, identify individual halos in a box. For example, this one, we zoom on this halo at 3 or 4 virial radii. I find all of these particles, trace this particle back to redshift 99, and identify the large random volume generated by these particles at that redshift. And we keep the large-scale mode at low resolution, but put all the computational power into this Lagrangian volume, plus baryons at very high resolution and run galaxy formation simulations. This is what we got by redshift 5. So the green shows the gas, and the purple shows the stars. So one of the advantage of our simulation is the physically motivated feedback models. And from the FIRE collaboration, this means the feedback in realistic environments. The simulation uses multi-phase ISM structure, which can resolve the hot phase, warm phase, and cold phase simultaneously. And we put physically motivated star formation and stellar feedback model and generate galactic wind self-consistently. And more importantly, these simulations run to redshift 0 are shown to be consistent with observations in many different galaxy properties. The part I'm leading is the HiZ-FIRE project, which is cosmological zoom-in simulations of galaxies at redshift above 5. We cover halo mass range from 10 to the 8 to 10 to the 12 solar masses, and we analyze these galaxies at redshift from 5 to 12. These mass range and redshift range are likely to be detected by JWST in the future. And the mass resolution for our simulation is from 100 solar mass to 7,000 solar mass for baryonic particles. So I shouldn't say this, but these are likely to be the ideal theoretical sample for studying galaxies at these redshifts. So this is the mock images I made for several of our simulated galaxies if these galaxies were observed by JWST near cam camera. This is res frame optical images, and the PSF I come up with 2 pixels. At the sanity check, we can calculate the broadband photometry for each galaxy and study the scaling relation between halo mass, stellar mass, and magnitude of different bands. This plot shows the UV luminosity function, which is res frame 1500 angstrom, from the simulations and from a compilation of observations. Surprisingly, we can do with and without dust, but our simulation agree very well with current data sets. This gives us more confidence about the suite. And then there are many applications to using this use these simulations to study galaxy properties and understanding their contribution to reionization. This is some of the old work I did with older simulations in the FIRE project, which we calculate the escape fraction of Lyman continuum photon for several dwarf galaxies. We find it's very sensitively dependent on the stellar population one uses. So we take the stellar synthesis model from the BPAS, which include both single star population model and binary stellar population model. The key difference from these two models are the ionizing photon production rate versus age of a given stellar population. The binary models predict more extended ionizing photon emissivity. So these photons are more likely to escape the birth cloud and finally escape to the IGM. So the escape fraction of ionizing photon from galaxies are higher, much higher when it's using binary population models. So another application for this simulation is the formation channel of present-day blue globular cluster, which we just do a case study in this paper that we find the merger of two proto-galaxies. The strong tidal shock just compressed the gas to very high surface density, above 10 to the 3 solar mass per square parsecs. And these gas can turn into stars at a 50% efficiency at of order free fall time, which is like 203 million years. And this star cluster form can survive for a long time until the end of the simulation. These might be the candidates of present-day blue globular clusters. There are many future applications, as I just described. The stellar mass-halo mass relation, stellar mass functions, broadband photometry, and luminosity functions. This is I just finished all of the runs and finished all of these analyses. Hopefully, the first paper of the new suite will come out soon, in a month or so. And some follow-up work include the IR emission. We can derive the obscure star formation fraction at this redshift and predict detection for ALMA deep surveys. This is the work currently in progress. Others, like the cold gas tracer, like the CCAT team and COMAP team at Caltech, are interested in looking at C2 emission and CO emission at these redshifts, and they are also interested in our predictions. Other things like the escape fraction of ionizing photons, since we have the new suite and we upgrade our code for radio transfer calculation, we can calculate the escape fraction using our new approach. Also, lemma alpha radio transfer, lemma alpha equivalent width, lemma alpha halo, etc. And cluster formation and metal enrichment, and many other applications in the future. Probably we also extend our simulation to the POP3 star regime at the low mass end, and also at the high mass end we extend to the first quasar studies. Thank you. We don't have black holes in this suite. Yeah, we don't. Yes, we worry about that, but since the most massive halo in our simulations is 10 to the 12 solar mass, so a black hole may matter at even higher masses.
Your globular cluster formation mechanism, L-star galaxies have hundreds of globular clusters, so does this mechanism actually happen often enough to explain that population?
Yeah, this is only one possible formation channel, since the blue globular cluster candidates are usually formed at, people say that these clusters form at very high redshift, but there are also other formation channels like nuclear starburst can do fragmentation, and those fragmented gas can form globular clusters. There are other formation channels in this happens. This is only one channel.
So I'm ecstatic to be here. because it's not very often in your career that you get to talk about a book. And this is the reason why the title seems so generic and general. It's because I wanted to share this labor of love with you that took me 2 years. It took me 2 years because I was racing against time to finish it before my baby son was born. And so I went to, the reason why this is very special for me was because I did my PhD actually at Colorado in supernova remnants. Most people don't know this, with Dick McCrae, who used to be here at Harvard. And I decided that wasn't going to get me a job. So I went around and I explored topics when I was at Princeton at the IAS. And I chanced upon this topic and I read Sarah's book. And years later, I went to her and I talked to her and I said, what do you think of me writing the follow-up to your book? And I thought she was going to give me 10 reasons why I was stupid to suggest that. And she was very positive and she gave me a blessing. So I started writing it. And this was roughly 3 years ago when I finished it. Here's a copy of the book. I brought an extra copy from Switzerland because I'm going to give it to the first student who comes to me afterwards with a student ID, proving to me that you are a student. So that's the prerequisite. Now I would like to walk you through the book and give you a flavor of what it does. So the point of writing the book was that when I was learning this subject from scratch, I had to read like 20 different monographs. For fluid dynamics, I had to read geophysical fluid dynamics. And then I was reading stellar atmospheres. And I was reading books on chemistry and so on. And I thought, no student should have to go through this torturous path, right? So one book can't teach you everything about everything, but it should teach you something about everything. And that's the spirit of the book. The book's trying to teach you something about everything that you need to know about atmospheres. So you start with, I don't have a laser pointer, but you start with a poor man's review of observations of exoplanet atmospheres. I say poor man because I'm a theoretician and not an observer. So it should give you some feeling of what the observations are telling you. Then there's a whole chapter on radiative transfer. And many people in the audience are experts. And there are many different ways to teach radiative transfer. And I've taken like 6 courses in my life as a student. And you could take a course on mathematical formalism, walk out and know nothing about radiative transfer. So this chapter is devoted to telling you what tau equals to 1 is. Right? Then there's a chapter that tells you what two-stream radiative transfer is, which is what I just talked about in the colloquium. There's a chapter on temperature pressure profiles. Here's another chapter that I'm very pleased with because in order to use a spectroscopic line list like high trend or high temp and transform that into an opacity function, it turns out the details are not trivial and they're scattered in like 10 different papers. So I collected all those details and I put it into one chapter. The other thing I had to teach myself was the chemistry. When I started doing this, I knew nothing about chemistry. And I thought, how could I, as a physicist, understand chemistry, right? So this is the answer to that question. And I'm going to show you that it turns out you can go very far on paper with chemistry. There's also fluid dynamics because I spent a lot of time thinking about that. It's very close to my heart, especially this thing called the shallow water system, which is marvelous. I had so much fun with it because the shallow water system is a 2D fluid dynamics, either on a plane or a sphere, and you can add all kinds of bells and whistles. You can add magnetic tension, magnetic pressure, you can add drag and rotation and radiation, and you still get an analytical answer. So you can use that to study wave modes and how wave modes couple. This is a quirky chapter. It's the de Laval nozzle, and I'll tell you why this is important. And there's the usual chapter on stuff that you should know as an astrophysicist and atmospheric escape. I want to point out that there are also appendices for things that you shouldn't have to look up in 5 different books, like vector calculus and thermodynamics and all the Gibbs free energies and Python scripts, because I don't know about you, but as a student, I learn from examples. So if I have a Python script, I can look at and I can reproduce that, I can learn a lot more. And the plan was to finish this quickly, do 300 pages, and then do a second edition in about 3 to 5 years when all of these topics are more mature. And my judgment is that these topics now are in flux, and one shouldn't put it in a textbook. So I've probably used a lot of time. So let's not talk about that. Let's go straight to chemistry. So equilibrium chemistry, solar abundance, pressure of 1 bar. This is the relative abundance by number. These are the 9 different molecules. This is temperature. And so these are the 9 different molecules with carbon, hydrogen, oxygen, and carbon CHON. And the dots are the full numerical calculations using something called a Gibbs-free minimization code. And these curves are fully analytical. And that surprised me that you could actually do equilibrium chemistry for 9 molecules fully analytically. And the error is better than 1%, the sub-percent level. So I found out that this is very useful, because if you can do chemistry using a Python script, you can build 90% of your understanding of the different trends. Like, for example, the dominant carbon carrier at low temperatures is methane. And when you get hot enough, the dominant carbon carrier is CO, unless you have quirky things happening like high metallicity or high C/O ratio. You can learn all of that playing with these models. And most of the intuition of chemistry can be built up from equilibrium chemistry, because this equilibrium chemistry is just equilibrium chemistry happening at a deeper part of the atmosphere. You can think of it that way. Opacities, I had a lot of fun talking to someone from the high trend team. I was delighted to have this conversation, because opacities are something that are very close to my heart. You need to do these radiative transfer calculations. And this book tells you all of the assumptions and the pitfalls for how to go from a spectroscopic database to something like that. So the opacities were different for water, CO, CO2, and so on. So the book tells you how to do this. Now, okay, let me go to the punchline. Why do you study this nozzle? You study this nozzle because it teaches you how flow reacts, how flow speeds up or slows down, depending on the Mach number. And the reason why this is useful is because it teaches you 3 things. First, it teaches you how shocks form, and it teaches you how flows behave in closed loops. The reason why I thought about this was because I was thinking about hot Jupiters. Hot Jupiters have permanent day and night sides. We think they are permanently irradiated on the day side. So the flow is actually going around and around in the closed loop. And the question was, do you form shocks? And so I started thinking about this, and I talked to a climate scientist, and he said, have you thought about nozzles? And so I started digging the literature on nozzles. Turns out the Russians had thought about this 50 years ago, because they were trying to build wind tunnels, and they were trying to avoid shocks forming. Right? So I went to the engineering literature, and I read up on these nozzles, and part of that effort is incorporated into this book. And the other really useful thing about nozzles is that if you take a nozzle and you tilt it 90 degrees on its side, this allows you to understand atmospheric escape. The equations that dictate how gas is escaping out of the gravitational well of an exoplanet are the same ones that are describing this nozzle. So if you understand the nozzle, you understand all these 3 things. I have time for 1 or 2 more things. So moving on to things that are more abstract, since I'm a theorist, there's this quantity that took me a long time to understand. This quantity is called the potential vorticity. This is sometimes misunderstood in the astrophysical literature. What we call potential vorticity in astrophysical literature is really the vortensity. It's the barotropic limit of a quantity projected onto surfaces of constant entropy. But the real quantity, the potential vorticity, can be projected onto an arbitrary surface. This means it has an arbitrary number of physical units, and because you can choose an arbitrary number of surfaces to project it on. The correct surface to project it on is the surface of potential temperature. The potential temperature is just related directly to the entropy. And the reason why you want to do that is because when you do that, you guarantee that the entropy is invariant. And this is a derivation I go through in the book, and this is a derivation that I learned from reading geophysical fluid dynamics textbooks. The reason why this is useful is that PV maps can be used to predict when instabilities happen. In fact, there's a whole literature in the earth sciences where PV maps are used to predict the occurrence of hurricanes. I still have a few minutes. In a future edition, something that I'm thinking about a lot, because I'm realizing more and more that as we move to smaller and smaller exoplanets, and we are thinking about secondary atmospheres and not primary atmospheres, meaning atmospheres that do not necessarily reflect the conditions of formation. And the reason why they are secondary is because they don't come from planet formation, but they come from geochemical cycles. So one such cycle on Earth is the carbonate silicate cycle, or the long-term carbon cycle. And I ran out of time, so one of the questions I'm asking is that, is this cycle, the way it's set up on Earth, general enough, and how does it work on other planets? I think this is something we need to really understand if you want to have a meaningful conversation about habitability on exoplanets in general. So this is it. I'm happy to take questions. Thank you. I avoided right, let me go back. So this is one of the things I avoided, biosignatures, because as you know, Sarah Seeger at MIT is working furiously on trying to collect a library of biosignatures. And I feel that this library hasn't crystallized yet. I think the work she's doing is visionary because it's not Earth-centric, and she's trying to make an exhaustive library based on basic chemical principles. The challenge, and this is, I go back to geology again. The challenge is, how do you distinguish this from geology? Because it turns out that rocks are very talented at using and making the same gases. So you can construct scenarios in which you can create abiotic oxygen and have it stick around for a long, long time. You would, I see what you're asking. I think the final answer is probabilistic. So you look at the planet and you collect all the details, like what's the architecture like, what's the UV environment, how much oxygen, how much ozone, how much water, and then you try to rule out some of these scenarios. One of the scenarios that's been explored by Robin Wordsworth, who's actually here at Harvard in the climate department, is that you could create abiotic oxygen by just photolysis. You can have water going very high in the atmosphere, you get photolyzed, you get oxygen. Ozone is a byproduct of oxygen, they come together. And you could create scenarios in which all the hydrogen escapes, but the oxygen and ozone just sticks around. So one way to tell is that if I point a UV telescope at this system and I see escaping hydrogen, I know, maybe this is the scenario and not life. Absolutely. There was a strange counter-argument to that published by Hanno Rein and Dave Spiegel and so on. And they suggested that you could have this, it's strange, right? But they suggested that you could have a planet that has oxygen, and then you have a moon that just has methane, and it's not resolved in your observations. And when you analyze them as one single source, it looks like they're out of equilibrium. I find that very, well, I think Occam's razor when I think that. To be clear, the book doesn't have all of these sophisticated details I told you, because when I wrote it, the thinking I had was the bulk of the book should not be outdated in 50 years. So it answers questions like, how do I understand hydrostatic equilibrium in 3D? How do I calculate a line list from quantum mechanical inputs and so on? So that's the focus of the book. So I didn't want to put in things that were going to make the book outdated, but one of the referees forced me to, and that's the chapter 14. And I caveated saying that this chapter will be outdated in 5 years, and the referee is Jacob Bean, so blame him. That's another question. Yeah, maybe the book will be digitized and you can see it through lenses. Thank you. Oh, sorry. My apologies.
Okay, hello everyone. So I'll talk give an overview of the work we have been doing with LOFAR. This is kind of preliminary work, so it's still ongoing, to hunt for basically AGN fossil plasma in galaxy clusters. And this is work done with the LOFAR Surveys Key Science project. So if we look at galaxy clusters in the radio, emerging galaxy clusters, we find these really complicated megaparsec size structures. These elongated structures here, and we call these elongated structures radio relics. So these are two images of two merging clusters, where in blue you see the X-ray emission, and in red you see the radio emission. And the idea is that these structures trace kind of merger shocks, which are essentially generated when these galaxy clusters collide, and then shock waves are generated. And indeed, shock waves have been detected with X-ray observations at the location of these radio relics. However, the Mach numbers of these shocks are very low. So it's an open question how these kind of low Mach number shocks can accelerate particles so efficiently, because we can observe these particles in the radio, and these radio sources are actually quite bright, in particular at low frequencies. So there are several models for how you can accelerate particles in the intercluster medium. The first one, the default one, is what we call diffusive shock acceleration, and this is kind of similar to what happens in supernova remnants, where particles cross back and forwards across the shock. And each time they cross, they gain a little bit of energy. And in this way, you can generate a non-thermal population of electrons, essentially cosmic rays, which then radiate synchrotron emission if you have magnetic fields present. So it's still a big question here how efficient this mechanism is really in the intercluster medium, in particular because these Mach numbers are low. And there's no real agreement about that yet. There's also another kind of mechanism, and that has to do with, for example, radio galaxies we have in clusters. So you could also think of starting, instead of like particles from the thermal ICM, so keV energy, you could also maybe start with particles which are already relativistic. And it's much easier to accelerate, of course, a particle which is already relativistic. And one, of course, a source of these relativistic particles are these tilt radio sources here, which you see. This is one famous example in the galaxy clusters where the jet are bent backwards. And just to illustrate that here, this is a very old review paper from Miley, and the idea is that this kind of, here you have a normal kind of FR1 radio galaxy, and when these galaxies move with respect to the ICM, these jets are bent backwards, and then you get this really extreme, what we call head-tail sources. So these kind of sources, they must deposit kind of plasma into the ICM. We kind of see that happening, and the question is essentially, what happens here? What is kind of the ultimate fate of this radio plasma? And one of the important things is that this radio plasma loses energy, because we see it in synchrotron, and also it loses energy by inverse Compton-Lossen. So this plasma should have a very steep spectrum. So it's very hard to detect at high frequencies, because steep spectrum basically means only bright at low frequencies and extremely faint at high frequencies. So we have to hunt for this kind of like fossil plasma with a low frequency radio telescope, and ideally go as low as possible as what we can do from the ground. And the best tool for that is the LOFAR telescope, because it has sufficient resolution to really resolve these kind of radio galaxies in clusters. So this is the LOFAR telescope in the Netherlands, and this is a little bit of a weird telescope. It uses phased arrays, but you can essentially think that these kind of like flat things on the ground, they just simulate a normal kind of like telescope by adjusting the delays. So you can think of these stations as just being telescopes. Not actually even one telescope, because you can make copies of the signal and even look in different directions at once. So actually you can think of it as thousands of telescopes if you have the computing capability. So this telescope operates in a range 10 to 250 megahertz, and that's kind of the lowest frequency range we can observe from the ground because of the ionosphere. Below 10 megahertz, basically, the ionosphere is opaque, and the radio waves are basically bounced off. So we did some first observations, kind of first deep observations with LOFAR, and we studied a couple of clusters, and one of these clusters was Able 2033. There was no really particular reason why we observed it, except that it was kind of located in a kind of easy part of the sky with a good enough declination, because LOFAR kind of has to look quite high up in terms of elevation. And it was in one of our pointings of a big survey we are doing. And this study was actually already studied. So I looked at this cluster before with the VLA and with the Westerbork telescope, and we already saw some hints of diffuse emission in the cluster. This is kind of a radio image made at 1.4 gigahertz, so kind of what we call high frequencies. And this is also known to be emerging clusters because it has been studied at X-ray and optical wavelengths before here. So just showing an optical image of this cluster here. So this is the optical image where you can see basically two BCGs indicating this is kind of a binary merge event. And that's even more clear when you look at this very nice deep Chandra observation from Matt Owers here, where you can even see kind of a shock front here. And you can see kind of the main cluster sitting here. And there's this extension here to the south of another merging component. And this is what we see with LOFAR. So this is quite different from what we saw at high frequency. So we see in extremely complicated situations of filamentary radio emission and mixed tilt radio galaxies. So from the observations here, we already conclude that if you start looking at galaxy clusters at low frequency, you see some kind of radio sources which are basically invisible at high frequencies. And we speculate here that this is probably the reason why this all looks so complex is probably there's interaction between the merger, the ICM, and the tilt radio galaxies, leading to this very complicated morphology. And here there's an optical overlay of this radio emission, where you see that probably this is one counterpart, this is one of the BCGs, and here there's another counterpart of this radio sources. But it's an extremely complicated situation here. This is connected, and there are wisps and tails, and we do not completely understand this yet. But it at least indicates that there is kind of like steep spectrum fossil plasma here, it seems. And another observation where we also look at is the cluster Abel 2256 is also a very famous merging cluster, a very nearby cluster. So this is the LOFAR image of this cluster. And this cluster was already known for having very complicated diffuse radio emission on megaparsec scale. So that's kind of the emission you see here. Now there's one interesting thing here. You have this extremely long head-tail galaxy. So this is an extreme version of a galaxy which moves probably with very high velocity with respect to the ITM, where basically the two jets bend back into one giant megaparsec jet. You see this very faint extension here. And the interesting thing is that this extension is not visible in the deepest JVLA observations. So this is a spectral index map of the radio where you indicate basically the slope, and old plasma basically has a steep slope, so it should be blue. And we cannot detect this emission at high frequencies, implying that the spectral index is really steep, so something like -3, which is quite spectacular because this is really rare. So again, indicating the presence of fossil plasma in clusters which you can not detect at high frequencies. And I think the most spectacular example we have come across till now is the cluster Abel 1033. This is work by Francesco de Gaspinin. This is also a merging cluster here. This is basically the galaxy distribution of the cluster. So that's basically the blue image where you again see a bimodal nature. Basically here's one component and here's the other component. And in red we have radio contours at 1.4 gigahertz. And the Chandra X-ray images are basically the white contours. Now, if we look in this image with the GMRT at 600 megahertz, which is already very low frequencies for many people here, we can kind of see this interesting radio sources here, where here we see again this kind of one of this example of a tailed radio galaxy, where you can kind of see the tail moving backwards. And if you now go to 300 megahertz and 150 megahertz, you suddenly see something new appearing here. Essentially, this extremely steep spectrum emission here, which are probably the extension of the tails of this galaxy, basically making these things almost 500 kiloparsec in length. And if you look at the spectral index here, which you can compute here, the spectral index is -4 or even steeper. So this is extremely steep. I'm not aware of sources actually which have this steep spectrum. So this basically proves that if you go to low frequencies again, there are really new sources appearing in galaxy clusters, which you have no way to detect at high frequencies. Because the funny thing is, if you do a calculation with this kind of spectral index, you would need 100 years of VLA time to detect this source. So simply no way. Well, this was a very short LOFAR observation. So this kind of sources you really can only detect at low frequencies. And the question is essentially, because this radio emission is actually quite bright, and this is still a puzzle, so we think actually this radio emission has to be energized by some kind of form, probably by the merger event again of this cluster, but the details are still not understood. And to summarize, so this is still work in progress, but I think it's already clear from this first observations what we're doing, that this really deep low frequency observations reveal kind of a population of kind of new or extended fossil radio plasma from radio galaxies. But we still need to determine really how common is this, because these were just a few random examples. It was not really a nice, well-defined sample, for example. And also, eventually, what is the volume filling factor of this kind of plasma? Because, for example, if you have shock presence, and this needs to interact with shocks, the larger the volume factor is, the easier it is, of course, to re-energize it and create these really large sources. And for that, for example, we are aiming to go to even lower frequencies, because with LOFAR, these observations I showed was at 150 megahertz, but we have antennas which can go all the way down to 30 and maybe even 10 megahertz. And there, more and more of these sources should appear, because if you have something like -4, you can imagine these sources must be extremely bright at those very low frequencies. And there's still an open question, essentially, what happens with this fossil plasma when you have a merger event? So this is still an open question, but I think this provides a very interesting opportunity, at least for particle reacceleration in galaxy clusters. As we really see now, there is this presence and there's this population of fossil plasma in galaxy clusters. Okay, thank you. Yeah, actually people have cross-correlated in some cases with Fermi observations for some galaxy cluster shock. And this all results in non-detection. It's actually quite interesting because this already suggests that the relative acceleration efficiency of protons and electrons must be different than what, for example, a DSA type mechanism expects. Because otherwise you should be kind of on the limit of detecting this kind of emission with Fermi. And Fermi does not detect it. So this is kind of an interesting clue that maybe it's not really classic DSA what is going on here, so it's something else. Yeah, it's a challenge to theory, and really there's really essentially input from theory is really needed here. Yeah.
So I'm trying to understand, I get how you can tell they're bent when they look like a chevron shape, but when they merge and they become sort of a single object, how do you know that that's not just a jet that you're seeing with an invisible counterjet? Like how do you actually tell between those two scenarios?
I mean whether they're really single side.
Whether so it could be just a jet where the jet is beamed towards us, the counterjet is beamed away from us, you can't see the counterjet. So how do you distinguish between that situation and the case where the two jets are bent into the same?
Right. So the crucial thing here is to go to really high resolution observations. So quite often what we see single jets at lower resolution, but when you need to redo this observation with higher resolution, you then hope to see essentially two jets being bent very close to the nucleus. There is still an open question whether this single-sided jet can exist, because there are a couple of these sources actually where people have done high resolution and they still do not see two jets, which is a bit puzzling. But for most of these cases, actually, when we do higher resolution observation, we do see two jets. Yeah.
So, how much benefit do you think would be gained by launching something into space and going much lower frequency than megahertz? And is that likely to be outrageously expensive?
So people are actually thinking about this. This is certainly not cheap, but it would be very interesting. So you could maybe, if you go to space, you could go to maybe down to the megahertz range. You cannot go much below that because at some point even the interstellar medium, or essentially our own galaxy or solar system, essentially is opaque to.
It's about 1 to 2 megahertz that quickly absorption of the interstellar medium cuts off any source.
Yeah. So this is kind of the limit where you can go. For example, people are thinking about placing something on the moon because the other problem here is interference. Like you're at the megahertz range where a lot of shortwave radio transmissions are taking place. So it's and also the sun is extremely bright and Jupiter is also an extremely bright source. So it's kind of a challenging environment, but it will also be very interesting, for example, to detect exoplanets. That would be in this kind of frequency range because most of the planets, even the Earth, for example, they kind of radiate very strongly at the megahertz range. So people are thinking about it, but it's certainly not easy to do.
The only time that it was done was back in the 70s with that photo program. They just released the wire. And there are some papers on the data that was collected. But since then, it could be a whole moving the field.
Yes. The other problem is, of course, resolution. You need really long baselines to get some resolution because these waves are like tens of meters in wavelength. So. But in space, you can in principle do that. And the other good thing about it in some ways that you don't need to know your spacecraft position very accuracy because you can make very large errors of meters because these wavelengths are so long that you don't have to care exactly where these spacecrafts exactly are. So you don't have to build a very accurate telescope in that sense. Yeah.
I want to ask, when the electrons accelerated inside the jet, or is it, there must be a shock, a bowl shock, that's ahead of the jet? Can you actually tell where those electrons are accelerated?
So so in some cases, so these are kind of tilt FR1 radio sources, what we call. You also have like FR2 radio sources where essentially the jets end up in really strong hotspots. Then you even see evidence of shocks there. Here we think actually that these electrons are just aging along the ledge. So they're accelerated in the nucleus, and then they're simply aged by synchrotron and in inverse Compton losses. So these, we do not really see evidence for shocks. We see, of course, evidence for merger shocks, but not shocks because of the jets itself. Yeah.
Thank you,
Okay, thanks for the opportunity to talk here. I'm gonna change the gear compared to the previous talk and go to a bit of early universe cosmology. And in particular, I want to talk about this, the work we are in progress that with Cora Dvorkin in physics. And the question we want to ask is whether we can look for signatures of extra particles present during inflation from clustering statistics of galaxies, in particular from power spectrum or bispectrum of galaxies. So just to set the stage, well, thanks to many different observations of CMB, supernovae, and large-scale structure, we arrived at a lambda CDM model where we have a simple model with where few parameters describe the composition of the universe and its evolution. But of course, there are several open questions: the nature of dark matter, dark energy, and the origin of primordial perturbations. And this last question is the one that we are interested in and we are trying to constrain. So in the standard paradigm in inflation, we have a phase of accelerated expansion where if we describe it where inflation is determined by a single degree of freedom, you can describe it by a scalar field where the classical dynamics of the field determines the background evolution, the homogeneity and isotropy, while the quantum fluctuations will source primordial perturbations. And the predictions of simplest inflationary models is that the primordial perturbations are adiabatic and they have a nearly scale invariant and Gaussian distribution. And the question that we are interested in is whether we can look for signatures of these extra particles through deviations from Gaussianity of the primordial perturbations. So what are we talking about? If we search for primordial non-Gaussianity, it will help us to understand the field content during inflation. So that's the interesting question, that even if inflation is driven by a single degree of freedom and you have only a single scalar field, in principle you can have extra particles or extra fields present during inflation. So the question is whether we can constrain the mass and the spin of these extra particles. And from a lesson learned from colliders is that when you're looking for new particles, of course, you look for their spin and the mass. Now, these massive particles, of course, if they were present and massive, they would decay outside the horizon during inflation. But their late time correlation functions is not directly observable. However, their presence can be, in principle, inferred from correlation functions of curvature perturbations or the inflationary perturbations that then we constrain from CMB or large-scale structure. So there has been recent work by Xiangcheng here and also by Arkani Hamed Maldesena, and a more recent update on that by Li et al., where the correlation functions of inflationary perturbations has been calculated in the presence of extra fields or extra particles, which in principle have mass and a spin. And the interesting point is that these correlation functions, in particular, if you look at the bispectrum of curvature perturbations, has a distinct shape. So because the particle has a spin, so you will, the 3-point function of curvature perturbations, if I could, will have a distinct angular dependence. So these are just Legendre polynomial of order s, where s is the spin of the particles. And also you will, if the particles have masses that are larger than 3/2 h, then you will also have this oscillatory behavior. And the oscillatory behavior has the information about the mass of the particle through this frequency, where the frequency, where this mu s is basically the mass of the particle, the ratio of the mass to Hubble parameter, and the spin of the particle. So it's a combination of the mass and the spin. So the question is that given this primordial bispectrum, in particular in the squeeze limit, where one of the wave numbers goes to 0, whether we can look for the signature of this, inflationary three-point function in the late time power spectrum of galaxies or the bispectrum of galaxies. I'm going to be talking about the constraint that we obtained from the power spectrum. And the other point that I should mention is that, of course, these particles the production rate is suppressed by a factor exponentially by mass over h. So if the particles are much heavier than the Hubble parameter, of course they would decay away and you would never see them. What is the best constraint on primordial non-Gaussianity of different shapes? So of course the best current constraints that we have are from CMB and Planck data, where they have constrained several standard shapes of non-Gaussianity, like local shape, equilateral, or orthogonal shape. And also they have set constraint on some version of the anisotropic bispectrum, which has this angular dependence. Now, our best hope of improving the constraint on primordial non-Gaussianity, apart from possible improvement from CMB polarization, is from large-scale structure surveys, given that the map is a 3D map compared to CMB that is a 2D map. Now, the observables that you can consider to constrain non-Gaussianity are varied. In particular, as I said, I'm interested in clustering statistics and in particular power spectrum. And the signature of non-Gaussianity on power spectrum will show up as a scale-dependent contribution to the bias. So this plot is taken from a paper by Dalal et al. In 2008, where they have measured the power spectrum from simulations that have primordial non-Gaussianity, the initial condition, let's say the non-Gaussian initial conditions of the local shape. So here, the black line, well, the lines are all similar color, but so you have like a Gaussian case, and then you have non-Gaussian power spectra for several values of the non-Gaussianity. Now, the takeaway home from this is just that when you have primordial non-Gaussianity of local shape, where you have quadratic corrections to the Gaussian gravitational potential, your halo bias, or correspondingly also your galaxy bias, will have a scale-dependent contribution at very large scales, so at very low k. Now, this is very nice for local shape. This is a very distinct signature because at very large scale, physics is simpler. You can model the bias as a linear bias, and this scale dependence that is induced by the local shape has this distinct 1/k² dependence that cannot be sourced by astrophysical sources, although there are also sources of systematics. Now, our point is that in the presence of the given shape of non-Gaussianity that is sourced by these extra particles, you can similarly look at the scale-dependent bias. And, well, it's too much equation, but I just wanted to say that this scale-dependent bias would be, in perturbation theory, well, one way of calculating it is that it would be integral of the primordial bispectrum, coming with, of course, with factors of the transfer functions. And in our case, we could, we could calculate this scale-dependent bias, and the scale-dependent bias will have dependence on the masses and the amplitudes that I showed before. So at the end of the day, the goal is to constrain the masses and the amplitudes. Now, if I look at the scale-dependent biases that are calculated, it's more complicated and less of a distinct signature than the local shape. So the cyan line is a local shape, which has this 1/k² at very large scale. In this case, first we had these oscillations that had a frequency proportional to the mass. So that's why we see this change of sign. And then also the other thing is that the K dependence is not, so it depends on the spin of the particle, and it's not necessarily a signature at very large scales, which means that modeling it is more complicated, because then you have to look at the scale-dependent contributions to the bias that are due to Gaussian contribution, and they have nothing to do with non-Gaussianity. But just in terms of understanding what is the simple scaling, if I neglect the oscillations and just assume that the transfer functions go to 1 at large scale, so let's look at the large scale limit of this. As I said, the local shape has this 1 over k squared term, whereas, for instance, the non-Gaussianity sourced by spin 0 particles would still have an inverse k dependence, so it is nice. It is a more distinct signature at large scale, and we will see that we can constrain the spin 0 massive particles better than the other ones. For spin 1 and spin 2, we will just have some power law scaling for the bias. So then as a first trial, let's just take this scale-dependent bias, and let's see how future surveys can constrain the mass and the amplitude of this non-Gaussianity, the mass of the particles and the amplitudes of contribution to the non-Gaussianity. So we do the usual Fisher forecast. We add some additional effects. So we add the linear redshift space distortions, and also we add the suppression factor that where the sigma v is basically the sum of finger of God, so nonlinear version of RST, and the redshift error of spectroscopic or photometric surveys. And we consider the case where we our survey only have a single tracer versus multi-tracer. And here is the result. So we consider Euclid as an example of a spectroscopic survey, and LSST as an example of photometric survey. So when we consider a single tracer case, the constraints on the C0 are of order 10 for Euclid, and they improve by more than a factor of 2 for LSST. The C1, as I said, is more difficult, and also its mass of spin 1 is more difficult, as the dependence is much weaker. Now, the interesting thing is that when you add another tracer to your analysis where it has a different bias, your constraints improve significantly. So just to sort of summarize this is that the accounting for spin 2, first of all, would degrade the constraint on spin 1 particles, just because there is more degeneracy between parameters of spin 2 and spin 1. But the multi-tracer improves it, and there is a caveat that in this analysis we have not accounted for scale-dependent contributions to the bias due to Gaussian loop contributions, basically due to nonlinearity, simply due to of gravity. And to briefly conclude, I'm running out of time, but just let me put it here, that the power spectrum gives us some information about particles with spin 0 and potentially particles of spin 1 and 2. And when we use multi-tracer technique, it improves the constraint significantly. The improvement depends on whether we consider only spin 0 and spin 1, or we add a spin 2 as well. Now, the other question that we are working on is what I said as a caveat, which is how about when you add a Gaussian scale-dependent contribution to the bias. And last but not the least, bispectrum might be a better candidate to look for signature of these higher spin massive particles than power spectrum, simply because you can look at multiples of the bispectrum and try to also constrain the angular dependence that this particular non-Gaussian shape has. So, thank you. I think it's a very good question. So this is sort of like if you are in a generic inflationary scenario where you have a weakly broken conformal symmetry, it has been shown that these bispectra are going to be very small. There is no way you can make them large, and also you will not have very large contributions, for instance, from spin-odd particles. So this was shown in this paper of Arkani Hamed and Maldacena. The recent paper that I pointed out, the Lee et al., what they did is that they said, well, let's break the conformal symmetry strongly, and let's work within effective field theory formalism and write down all the contributions that can give rise, that are basically allowed by the symmetry, by the amount of. And the interesting thing in this is just that then, because the couplings that you are introducing when you are broken, when you have a strongly broken conformal symmetry are not constrained anymore, in principle you can say that it's true that you have a suppression factor, but also the coupling can be very large. There is no limit on the coupling. So in principle, the amplitude can be large. And another interesting thing is that in the case of the strongly broken conformal symmetry, you can also have contributions from spin-odd particles at leading order, which can be as large as leading order as large as the even spin particles. So for us, we took the bispectrum calculated in the second paper as a template, saying that let's assume the amplitude can be large and let's associate a free parameter to it and see how well we can constrain that parameter.
These particles or their descendants cannot be the dark matter. They definitely are unstable.
Yeah, these are just extra fields that can in principle be present, and yeah, it's not a dark matter candidate.
What does the redshift evolution look like for these scale-dependent bias? Does it follow the kind of more normal bias curve, or does it do something different?
So what we did, basically, so you will get the redshift dependence automatically when you do the calculation accounting for the redshift dependence of the power spectrum and redshift dependence of the biases, the Gaussian biases. So for this analysis, we took the usual assumption that the linear bias has a redshift evolution of square root of 1 plus z, for instance. So I don't know exactly at the end what is, I cannot say if it is a power law in redshift or no, because you have the growth factor with some redshift dependence. So it's a combination of all the redshift dependencies that come into play.
I'm a little bit more accustomed to thinking of measures of non-Gaussianity in terms of the FNL parameter.
Mm-hmm.
And I'm just wondering if the formalism that you walk us through can be roughly translated to values of FNL, which are now bound with Planck to ground values of 4 or so, if I recall correctly.
So, right. So
where is the interesting threshold? How far do we need to push down FNL to test some of these ideas?
Well, I think with these, it's a little bit hard to say how large in principle this FNL can be, because this framework of EFT is not for a given model of inflation with these particles that tells you, well, the couplings are constrained to be this much, so the total FNL should be of this order. So it's much more difficult than for instance, FNL local that we say, or the unity constraints on FNL will tell us, will allow us to, let's say, constrain very heavily the single field inflation model. So in this case, connecting this template, which is for us, we take it more of a phenomenological template, or that is not basically directly related to the models, which tells you how large should be the size of this FNL. So answer is, I don't know what should be. What is the expected value, let's say, of these amplitudes? Because the FNL with a combination of the amplitudes, which is related to the coupling of this extra field to the inflaton field, and some extra factors, basically, some extra mass-dependent factor. So as of a number, it's an interesting question, but I don't know what is a reasonable number.